I'm delighted to introduce our first plenary speaker, Dr. Pamela Harris. Dr. Harris earned her BS in mathematics from Marquette University and her PhD in mathematics from the University of Wisconsin-Milwaukee in 2012. She is now an associate professor at Williams College. Her research is in algebraic combinatorics, where she has published over 50 peer-reviewed articles. Dr. Harris is an award-winning educator and scholar who has been honored for her accomplishments in both areas. She received the 2020 MAA Northeast Section Award for College University Teaching, the 2019 Henry L. Alder Award for Distinguished Teaching, and the 2019 Council on Undergraduate Research Mathematics and Computer Sciences Division Early Career Faculty Mentor Award. Dr. Harris is also a fellow of the American Mathematical Society and a fellow of the Association for Women in Mathematics. She's also in the inaugural class of 2020 Karen Uhlenbeck Edge Fellows. In addition to all of these accomplishments, Dr. Harris co-hosts a podcast called Mathematically Uncensored and is the president and co-founder of Lathisms, Latinx and Hispanics in the Mathematical Sciences. It's with great pleasure that I introduce Dr. Pamela Harris.
Thank you so much, Christine. It is such an honor to get to chat with everyone about some math that I really love. So I'm going to go ahead and share my screen. All right, how does that look? Is that visible to everyone? Okay, and then I'm just going to make the little box a little bit bigger on my end so I can see more faces. So thank you so much for having cameras on. It's always a little disheartening when you give a talk and then they use a platform that you only look at yourself. So I'm really glad to just see so many people. It actually feels like I'm in a room. There's people there and they're waving and they're smiling. So this is just awesome. Okay, so I want to tell you the story of how I got into these objects, studying these objects called parking functions, which I do not expect anyone has ever heard of, because in fact, as somebody who studies combinatorics, I didn't know about these things until relatively recent. So the first thing I'll do is I will tell you about what those objects are. And then I want to give you some ways in which we've generalized them, right? So that's kind of a common thing that mathematicians do. You study something and then you say, how can I make them more general? And then you study that thing. And then you ask again, can I make them more general? And then you study that thing. And then you iterate. And then you have a quite successful research career that has paid off dividends for me every time I try to generalize. And so my goal is to leave you with some questions that you might want to ponder and some math that you might want to work on with others, with me, maybe not with me. That's also okay. And because I know that I speak fast, sometimes a little too fast, and I get very excited, and I don't want you to feel like you have to screenshot or, wait, where do I find what she was just talking about? I created this Padlet. So I put that in the chat for you. And so that looks like this, and I hope you can see that. So there's some articles in here that introduce you with a lot more details to all of the things that I'll be talking about today. And then I also wanted to throw in some opportunities that you should know about that are upcoming. So if you're looking to apply for an REU, you want to read some more papers, notice that there's a paper that I wrote with some students with the title of the talk. And then tell you about some of the programs I'll mention. And in fact, I'll be at ICERM this coming summer running a program that studies parking functions. So you're getting, some scoop here about that information. And then also you might be earlier on in your career and you're like, what is a research experience for undergraduates? I'm a first year or a second year student. Well, there's some opportunities for you. And so you can click on here to find those. And then you might be like, wait a minute, how do I even do this? You can get some advice from students who have just applied and been successful into getting into REU programs. So their advice is here. And because always Black Lives Matter, you should go check out Mathematically Gifted in Black. You already learned a little bit about Lathisms. You also might want to learn about some Indigenous mathematicians. You might want to listen to me chat with my co-host Eris Winger on Mathematically Uncensored. You might be like, wait a minute, what is all this nonsense about graduate school and REUs and how do I present myself? What do I do at conferences? You might just be like, what are the norms of the math community? You can come to a webinar. And then there's Asked and Answered, a book that I wrote with Eris. And then also, if you're like, well, combinatorics is not my cup of tea. You might want some other type of math research. There's a book with a whole bunch of projects that you can read about. So just lots of resources that I wanted to share with you as you listen to me talk, or you might, it's okay. You might peek at some of those resources in the meantime, if I bore you. All right. Also, I'll have the chat open. So if you have any questions at any point, please pop them in there. I think it'll trigger my attention enough that I will see them. But if one of the organizers sees a question and I skipped over it, please, please, please just stop me at any point. All right, are we ready? Okay, let's do it. So let's start with parking functions. Now, luckily for us, parking functions actually involve cars. Sometimes in math, you name things and then they don't involve the things that, the names are after. So here's the setup for the game that we're going to play. We're going to have these little cars. They each are numbered. So car 1 all the way through car n. And they're going to enter a one-way street. The one-way street has n spots. So the exact same number of cars has the same number of parking spots. And they're numbered consecutively from left to right. So 1 through n. So here's how the game goes. Each car is going to enter a parking spot and it's going to have a preference. So just like you might go to the grocery store and you have a spot that you really like on that one-way street, maybe close to the door, maybe not. Okay, you go to that parking spot. If it's available, you're going to park there. If it's not available, you're on a one-way street. So you're just going to continue down the street until you find the first available parking spot and you'll park there. How does that feel? Okay, so the first car enters, goes to its preferred spot, parks there if available, otherwise continues down the street, parking in the very next available spot. Then car 2 enters, then car 3 enters, and they all follow the same procedure. All right, great. So here's a question. If I know all of the preferences of the cars, how can I tell whether all the cars are able to park on the street? That's the question that we're interested in answering. Okay, so you know the preferences, and you know how they're going to enter and try to park on the street. How do you know whether they actually can park? So if it happens that the sequence of preferences allows all the cars to park in the first n spots, then we call that sequence of numbers a parking function. That's it. That's a parking function. So first few minutes, you now know what a parking function is. Okay, great. Yeah, definitions are rough to parse though. I prefer examples. So the lesson learned is when you have a definition, the first thing to try to figure out is, wait, what is an example of such a thing? And what is not an example of such a thing? So let's consider the case where car 1 prefers spot 1, car 2 prefers spot 1, and then the third car prefers the third spot. Okay, so notice that I'm keeping them in order. So the first entry is the preference for the first car, the second for the second, the third for the third. Okay, so only 3 cars, 3 parking spots. Let's see how this proceeds. Car 1, well, lucky duck, always gets what it wants. First spot. Car 2, now notice, car 2 would want this spot, but it is occupied. So it continues down the one-way street and it parks in the first available. Sorry, we're getting that little message there. Okay, so spot 2. We're okay? And then car 3, okay, what did car 3 want? They wanted spot 3. It's empty, so it'll go there, and ta-da! Success. 113 is a parking function. Not too bad, right? Okay. And then we consider a very small change. 313. Okay, we play the same game. Car 1 always gets what it wants, got the third spot. Car 2 enters the street wanting spot 1, which is empty, so it takes it. And then car 3 enters and it wants spot 3, but that one's occupied. And so car 3 can't park because again, we're on a one-way street. And so we say, oh, sadly, 313 is not a parking function. Okay, so now we have an example of something that is a parking function, something that is not a parking function. And now we have audience participation time. Because I know you all came ready. I mean, you're at a math conference, so I'm sure you have paper and pencil somewhere. And the question is, I give you these 2 preference lists. Pick one of them, and then decide whether the cars can park or cannot park. How do we do? Anybody have an answer for the first list? You can use a chat if you want. You can also just send it to me if you're a little shy. I know I would be shy. I wouldn't want to scream an answer because I always worry. And so you can also just private message me. Ah, somebody got a yes for the first and a no for the second. Yes for the first. It is a parking function. I think the first one is yes and no, yes and no, yes and no. Okay, great. This is awesome. Okay, yes, yes, yes. I think everyone's right. So the first one should be a parking function and the second one is not. Does somebody have a quick way to explain why this second one is not a parking function? Why is this one not by inspection? Like you inspect it and you're like, aha, this thing is not a parking function because no one wants the first space. Who is this? Bridget, we're sending you a complimentary parking function chocolate bar. I don't know. I don't have those. We'll make some. Okay, great. Yeah, nobody wants the first spot. So every single car is going to pass up the first spot and there's only 7 spots. So guess what? There's not enough spots for the 7 cars to skip the first one, right? Okay, great. Hopefully what you did, or maybe what I imagined that you did as you were thinking about whether these things are parking functions or not, you probably did the process that I did, right? You drew 7 lines and then you started putting the cars in there. What if I gave you 100, like a list with 100 numbers? Would you want that to be the way to do it? No, you probably are starting to think like, how can I do this more efficiently? So luckily for us, there's a result that says the following. So suppose I give you an initial preference. So just like these ones here, let's call that A1 through AN. What I'm going to do with that preference is I'm going to order the numbers. Okay, so I'm just going to put them in order. They're going to be non-decreasing because, well, they might repeat, right? So I can't say increasing because they don't always go up. They might be non-decreasing. Okay, then the result says the following. The original preference vector, so the thing you started with, is in fact a parking function if and only if the thing that you rearranged satisfies that bi is less than or equal to I for every index I. Let's put that into practice with these 2 vectors that we started with. So here's the first one. So what do? I'm going to rewrite this vector in order. I do that on the left column. You see that? There's a 1, the next number is a 2, then 2 4s, then a 5, and then a 6. We're okay? So first column, I just rewrite them in order. And then on the right column, I literally just put 1, 2, 3, 4, 5, 6, 7. And then I put the inequality that I need to satisfy. So this one. And then do we have any contradictions? No contradictions? Good to go, a parking function. And now you'll immediately see the problem with the second vector. Because in the second vector, if I order these numbers, immediately I see an issue with the very first inequality. 2 is not less than or equal to 1, not a parking function. Okay, so this allows us to quickly test whether a vector is in fact a parking function or not. Great, so now we have a way to kind of be a little bit more efficient and do it faster rather than having to like draw out the full picture of how the cars park. So now the question is, okay, great. How many parking functions are there if I know that I have n many cars and the same number of parking spots? So luckily for us, we can think about some examples of things that are always parking functions. So take, for example, permutations. Do we know permutations? So just all the possible ways in which we can order the numbers 1 through n. Why is that going to be a parking function? Well, there's no competition for spaces. Every single car wants a unique parking spot, and they're going to park precisely wherever they want to park. So all of those vectors that are just permutations are going to be parking functions. Great. Well, we know there's n factorial many permutations, so we know there's at least that many parking functions. Okay, great. Here's a formula that looks a little scary when you look at it, but it allows me to count the number of parking functions using what we call a recursive formula. So think Fibonacci numbers, right? How do we do Fibonacci numbers? You add the previous 2 to get the next one. This is something similar to that. So what you can do to prove a formula like this is you say, okay, suppose all of the cars have parked except the very last car. And the last car wants to park in spot I, some spot in the street. Well, that means that some number of cars parked to the left and some number of cars parked to the right. That's exactly parking functions on a smaller parking lot, I minus 1 on the left and minus I on the right. And then I have to choose which cars go to the left and which cars already get to the right. So that gives me this binomial. And then there's some choices for where the last car parks. So anyways, a little convoluted, but this is the way that people start counting things, right? They say, okay, well, how many could there possibly be? Can I give you some approximation? And then maybe we think, well, how would we build them? Oh, okay, maybe all the cars park, and then I got to just consider what could happen to the very last car so that it can park. And then I use a recursive formula. None of these are ever the goal. The goal is always, at least as a combinatorialist, is to give a formula that does not require me to know the previous numbers. So we call usually those a close formula. So something that just involves, I don't know, square roots, exponents, multiplication, addition, right? That it doesn't require a whole lot of processing. I just plug in the number and then do some arithmetic and ta-da, I know how many parking functions there are. So in fact, in 1974, Pollock gave a beautiful proof that enumerates, meaning just counts, tells me how many parking functions there are. So in that case, it just happens to be n plus 1 with an exponent of n minus 1. That's how many parking functions there are. I gotta tell you a story. The proof is real short. It's 6 sentences. And I've been working on parking functions since like 2017-ish. And every time I read that proof, I'm like, yeah. And then I'm like, no, what? Like, it takes me so much brain power to try to dissect what he put just like so succinctly. And so a year and a half ago, I was working on going through the proof yet again with my student, Kimberly Hadaway. And then I was like, Kimberly, this is enough. I've had enough. Can we write something that actually explains how this proof goes with a lot more detail and examples? Basically what we did on the board to try to understand that proof. And so we did, and then we wrote 2 articles about it. So that recursive formula I showed you, we write all the details that I said in like 30 seconds in one article. And then we do an article that explains this proof that Pollock gave. So that's in the Padlet. So you don't have to write anything down. If you find that, oh, I can probably put it back in the chat in case you want to play around with that. So there's the Padlet, but the 2 articles are there right at the beginning. So if you want to check those out, highly encourage you to do so. Okay, so now the next question should be, or, you know, I get this a lot. I'm a combinatorialist and people are like, well, what are the applications of parking functions, right? And I'm like, well, I like to enumerate things. Sometimes I don't worry so much about the application, or I think somebody else will apply that. I'm here to count things. But the truth is that parking functions actually started in computer science. So the people that defined them, they were interested in what are known as hashing functions. And so it's the way the data arrives into servers. So a computer does exactly this, right? A computer is trying to get information into a server. If that one is unavailable, it tries to get to the very nearest one. And so then it becomes a counting problem. So that's where it started. But of course, now we're interested in it from a combinatorics perspective. There's also connections to group theory, discrete geometry, hyperplane arrangement. And like I said, it all began in computer science. And so lots of different directions come together to study these objects. And now I want to think about, great, we know parking functions. We understand how many there are. What other things could we do with them? How might we generalize these objects? And so here's some things that people have done. All right, well, first off, why do we have to have the same number of cars as parking spots? Couldn't we have more parking spots? Maybe there's, 3 cars and 10 spots. How many parking functions are there? That's one option. Another is, well, not all cars have the same length. Maybe there's motorcycles and then there's semi-trucks trying to park on this street, and they all have a preference, but they also have an associated length. So people have studied that as well. There's also a case that I worked on with some collaborators where we imagine that the cars arrive after a night of construction, and some of the spots are actually just blocked by, trailers or whatever construction equipment is there. So, but they still could prefer that spot. They don't know that there was construction overnight. So how many ways could you still park these cars? So you can think of obstacles or potholes or whatever you might want to think about in that case. And we call these parking completions. So we wanted to complete the cars into the available parking spots. And then the other thing is, in reality, when I go to the store, I want to park near an entrance. Most of the time there's multiple entrances. So I actually have certain preferences. Sometimes I'll pass up a parking spot, even if it's available, because I'm trying to get to my second favorite parking spot. And so people have looked at that. They've looked at having multiple parking preferences. So each car can have a set of them. Okay, and I want to show you a version of that because this is what Kimberly was working on, who actually, and I'll tell you the story, she actually came to this conference last year when she was working on her thesis, and she had just finished those papers that published in that magazine. And she came to the conference and she was starting to share her initial research, and a conference professor that attended, so Dr. Shanice Walker, said to her, "What happens if you do this thing?" And then Kimberly said, "Oh, I don't know. We haven't thought about that." And that question became her undergraduate thesis. So you'll see very quickly how the connections you make at a conference, which was also virtual, right, can actually really, really shape the direction that your research takes. And then you'll see in a second how many other people have been affected by that question that Dr. Shanice Walker asked Kimberly as she was at this conference last year. Okay, so let me tell you the generalization so that you understand the question she worked on. So here's what we're going to do in this case. We're going to keep the number of cars the same as the number of spots, just like what we started with, okay? So 5 cars, 5 spots. The street is going to be laid out in the exact same way, just a one-way street. But what we're going to imagine now is that cars have a different type of preference. And this looks really convoluted. Let me just say it in words. You're going to tell me the starting position you're willing to park in and the final position that you're willing to park in. Basically, an interval. You're just going to say, I'm okay with parking in spots 3, 4, and 5. You don't get to skip 4. Is that okay? So you tell me the starting position, basically like your threshold, the starting position, and then up to the end, but you don't get to like X out any in between. You just want anything in that little range. That's what this whole nonsense here says. So you give me a preference. The A's are the beginning preference of the car. Okay, so this A1 is the initial preference of car 1. The B1 is the final preference that car 1 is willing to tolerate parking in. Are we okay with that? Right, so I have to give you those two, the beginning and the end. Okay, so let's consider an example because again, we want to see some examples, right? So here's a preference vector. I don't know that the cars can park. Oh, what if none are open? Yeah, then nothing can park, right? It's like if everything is occupied, then we won't be able to park. Great question. So here's a potential preference. Notice that I haven't decided whether the cars are gonna be able to park. I'm just defining what this would mean. So this means that car 1 is happy parking between spot 1 and 3. And that can include the 1 and the 3. Car 2 the same, car 3 the same. So they're just happy if they park somewhere on the street. That's what this vector says. Are we okay with that? All right, check. That one works. Look at this one. This one does not work. Why? Let's think about how the cars are actually going to try to park. Okay, because now if they can park, we will call it an interval parking function. Would they park in the first spot available in the range? Oh my gosh, yes, Audrey. Yes, the parking rule is exactly the same. So they will always go to their preferred spot, their first preferred spot. If that one's occupied, they continue in their interval, parking in the very first available. But if all of their interval is occupied, there may be empty spots after that. They don't tolerate those. They're out of the game. They're like, I'm too far away. Like that, I'm not willing to walk that far. Okay. All right, so let's look at this one. I claim that this one will not allow the cars to park. So let's try to follow the logic here. let's consider the first car. So the first car wants to park starting at position 2, and it will only tolerate that parking spot. It's really picky. It only wants spot 2. That's actually not so bad because it's the very first car, and we know that the very first car always gets what it wants. So in fact, it'll park in the second spot. Okay, so in your head, think second spot, gone. Now let's consider the second car. The second car wants that spot. It's already taken. And guess what? It will tolerate no others because its final preference is also spot 2. Already car 2 cannot park. Are we okay with that? Okay, so second spot taken by car 1. Second car wants that spot and will tolerate nothing else. And so the cars cannot park. All right, so now we would ask the exact same question. And in fact, somebody else had answered it. So the question would be, if I know the interval that the cars want to park in, how many such interval parking functions are there? And notice that you see this n+1 raised to the n-1 coming up, and then a factorial showing up, okay? So how does this go? And again, you can read some of those papers that I highlighted if you want like the actual proof with details and the examples, just because I go a little fast here. But let's think about what happens. Consider the initial preferences of the cars. So that's like the first parking spot that they're willing to tolerate, okay? Like I want that spot. Then each car is going to park in some spot because I am assuming that they were able to park, okay? So suppose that they end up parking in parking spot P sub I or P sub I+1 all the way to some P sub N. Well, if they park in that spot and the car wanted to park in that spot, their threshold better be one of those numbers. Their final threshold has to be one of those numbers. Otherwise, it would have parked outside of its interval. And then what we do is we start multiplying by a factorial for the number of options for each of those cars. And so there's n factorial many options for the possible final positions that the cars are willing to tolerate. And then each of them, you start with a parking function. That's the starting positions. And then you multiply by that n factorial. So convoluted. There's a lot there. But again, you can dissect it a little bit further in those articles. So just kind of giving you a very crude sketch of the proof. Okay, so now let's specialize even more. So we knew how many interval parking functions there were. And when Kimberly was presenting her work, Dr. Shanice Walker said, what about if they only wanted either their preferred spot or one right after it? That's it. Like you restrict the kinds of intervals you consider. So either their favorite spot in the world or just the one after it. How many of those things are there? And, Kimberly came back and she said, this was a good question and I don't know the answer. And she was like, is it done? And I was like, I don't think so. Let's work on it and see what comes up. So here's how the preferences go in that setting. So again, the cars have some favorite spot and they're willing to park either in their favorite spot or just one away from it. Okay, with the caveat that if you prefer the last spot, well, there's no spot after that. That's, a little technical wrinkle there. Like if you prefer the very last spot, you better just get that one because there's no more spots after that. Okay, great. So that's what this B sub I equals N for if the initial preference spot is N. So just a little wrinkle there. And then let's consider which intervals show up. So for example, this one works beautifully because if you notice, the first car will tolerate parking in spot 1, that's its preferred spot, but it's willing to park in spot 2. So the difference between those two numbers is 1, okay? So preferred spot 1, willing to park in spot 2. You look at car 2, wants spot 3 and will not take anything but it. Okay, that's great because it's the third spot and there's nothing after that. And then let's look at the third card. The third card wants spot 2 and will tolerate nothing past the third spot. So we're okay. One that doesn't work is this one. Why? Well, 2 is the preferred spot for the first car. It's willing to park one spot away from it. That's okay. The issue comes in with the second car. It wants spot 1, and this interval says that it would be willing to park all the way to spot 3. That is not a unit interval. It's allowing a lot more. So that is one that we will not consider. Are we okay with that? All right, I see some head nods. Okay, so let's suppose that we start with a unit interval. And now the question is, how do we guarantee, like, what must be true about the alpha and the beta so that we ensure that all of the cars can park? All right, great. Let's see some examples. So we already know that this one is an interval, a unit interval. And now we just want to determine whether the cars actually can park. So where does car 1 park under this unit interval? Car 1 parks in spot 1, right? Because it enters spot 1 parks there. What about car 2? Parks in spot 3. Great, because it was available. And then the third car, and I'm seeing it in the chat, the third car wants spot 2 and it was available. Okay, great. So they got exactly what they wanted. And then I love this in Venezuela. You say how many parallel parkings will occur for a preference interval or parking function? So like you mean allow 2 cars to park in the same spot, kind of like in parallel? Is that what you mean? I pause for clarification. Oh, between 2 cars that are already parked? No, I mean the normal parallel parking in. Oh, you are about 5 minutes ahead of me. I'm gonna come back to your question, and you're gonna see that that's a different generalization. So you're like, you are thinking like a student that came up with a question 3 years ago that has fueled so much research. So you're like, you and I are gonna talk as well, because you have a gut. You have a math combinatorial gut that I love. Okay, so I'll get back to that one in a second. Okay, but this is interesting because notice if the preference vector for the initial positions are all distinct, so if all those numbers are distinct, we're back to parking functions. And all the cars, there's no competition. They get to park exactly where they want. So this one ends up working because of that. And then here's one that doesn't work. And what happens in this one? The first car takes the second spot. We're okay with that? Because it gets always what it wants. Then car 2 comes in and spot 1 is open, so it takes it. But then car 3 comes in and spot 1 and 2 are already occupied and it wanted spot 1. So what would be the very first available spot that it could park in? The third spot. However, it only tolerates parking in spot 2. And so it fell out of its interval, and this thing is then not a parking function. And in fact, there's a word for that. So how many cars fell out of their interval is what we call the defect. And so this thing is often referred to as having defect 1. Like it's almost a parking function, only 1 car fell off. And there's been research that studies parking functions with some fixed number of cars that fall out of their interval, okay? So defective parking functions. Okay, so now it's gonna feel like I'm gonna do something completely different for just a minute. And the beautiful thing in combinatorics is that if I'm bringing a new family of objects into the story, you're gonna find out that they're exactly the same story in disguise. That's like, I'm just giving it away, okay? So we started all these unit interval parking functions, and then you're at a combinatorial talk, and then somebody's like, okay, now let me tell you about these other objects. And then the punchline is always, they're the same. Okay, here we go. So I want to tell you of these new things. They're called Fubini rankings, okay? And basically they are allowing for a set of competitors, say in a race, to be able to tie, okay? They can tie. And so here's an example. So first participant in this race earned first place. The second participant earned 5th. Then participant 3 and participant 4 tied for 2nd place. And then the 5th participant earned 4th place. So you might make a little drawing like this, right? You've seen these at the Olympics. They're like gold, silver, bronze, right? And then sometimes they tie. Wait, do they tie at the Olympics? I don't even know. I'm making stuff up. I don't even watch sports, but you know, just go along with it. In this particular kind of thing, they are allowed to tie. But here's a wrinkle that shows up. Notice that if competitors 3 and 4 tied for second place, they're basically covering second and third place. So this is why third place is empty. The next available rank is fourth place because there are 3 people ahead of them. Does that make sense? Okay. And that would be the case even if competitor 1, 3, and 4 all tied for first place. The very next available rank would be rank 4. Okay. So Fubini rankings are a little tricky. There's a little wrinkle there. Not a problem, but that's their definition. Okay. So here's the main theorem that Kimberly was able to prove. If you give me a unit interval parking function, she created a map that converted that vector, that preference vector, into a Fubini ranking. And then she gave the inverse of that function. She said, oh, well, if you give me a Fubini ranking, I can unravel it and create a unit interval parking function. So when you have 2 sets, right? Set A, set B, and they're finite sets, and you create a bijection between them. That means that the sets have the same cardinality. There's the same number of objects in both sets. And so we call that in combinatorics, we say that 2 combinatorial families of objects are equinumerous, meaning equal in number. Okay. But I really like it because it sounds real fancy, right? You're like, yeah, our sets are equinumerous. And then you like drink and sip tea and stuff. Okay, anyways, so that's one of the main results in her thesis. So she was able to give this bijection between the objects. This is great because remember the question that Dr. Walker asked Kimberly, how many unit interval parking functions are there? Well, the same number as Fubini rankings. And those had a formula. So you see how now you get like for free a result? Because you just say, oh, look, they're the same number as these other objects, and those other objects had already been counted. And so that's this formula. And notice it's intense, right? There's like a binomial and then an alternating thing. So there's powers of -1, and then you raise the binomial to n, and oof, they're intense. So these numbers that arise, so 1, 3, 13, 75, and so on, also go by the name either Fubini numbers or ordered Bell numbers. Okay, so if you want to learn more about them, do y'all know about this beautiful website? Oh, I can't believe I haven't talked about it. This website is what dreams are made of. Not because it's fancy, but because it holds so much knowledge. Okay, so like I dream of days when I get to input a sequence into the OEIS. So if you find a sequence that nobody has studied before, and you have something that is counted by those numbers, you can put in a sequence into the OEIS. So, have that in your back pocket anytime that you're counting something, because it'll allow you to connect your work to much, much other stuff that people have studied. Okay. All right. And I'm surprised, I need to put that one on the Padlet. Okay, great. So now let me go back to this question about the parallel park. So the story goes like this. So in 2018, I go visit my dear friend, Katie Johnson and Eric Insco at Florida Gulf Coast University. It was their summer program, and I got to meet one of their students, Allison. And Allison said, oh, I have this question about parking functions that I'm not actually going to work on, but I thought about, and I know you have some research students, maybe you want to work on it with them. And I thought, oh, that's very kind. First off, people don't usually just go around giving you open problems. I should make that clear. Let alone a student. But she was just like, I thought of this problem and I'm not going to work on it. So how about you think about it? And I was like, okay. So here's the way that she defined what she called Naples parking function. So like Naples, Florida. And then I'll tell you, I wish we weren't being recorded, but I'll tell you why she called them that in a second. So the story goes like this. You have the same number of cars as parking spots on a one-way street. The cars go to their preferred spot. If it's empty, they park there. If it's occupied, it's like they're going to parallel park in the spot behind. Because what do you do when you parallel park? You literally pass up your preferred spot to then back into it. Yes? So it's like you back up into the spot that you want. So the rule is, again, go to your preferred spot. If available, you do the normal thing, you just park there. If it's occupied, then you back up to check the spot behind. If that's empty, you parallel park into it. If it's not, then you just continue down the one-way street and doing the same thing, trying to find the first available. We okay? All right, so that was her question. And then I said, okay, well, this is interesting. So I was just thinking, and I was like, well, if we don't have to back up and we can park, then being able to back up makes more possibilities happen. Yes? So it makes me think that if I'm a parking function, I certainly will be what she called a Naples parking function. Meaning if I can park without backing up, then I should be able to park if I'm allowed to do something different, right? That's less restrictive. So that's exactly the proof. So if every car can park without needing to back up, then they can park if you allow them to look one spot behind. It just gives them an additional option. All right, great. So is the converse true though? Is it true that every Naples parking function is a parking function? And in fact, it is not true. And we've seen an example. So we've seen 313 not a parking function. Why? Do you remember the ordering thing? If I order them, it goes 1, 3, 3, and it better be less than or equal to 1, 2, 3. But 3 is not less than or equal to 2. So you could do it that way. But we also parked the cars. Remember the third car kind of fell off the cliff? So not a parking function. But now let's look that it is a Naples parking function. So car 1 enters street, 1 spot 3 takes it. Car 2 enters street, 1 spot 1 takes it. And here's where the parking rule for the classical parking functions would have failed us, because car 3 would have gone to its preferred spot 3, and then that one's occupied and would have continued forward. But under the Naples parking rule, car 3 goes here and then backs up, parallel parks into the spot number 2. So we are a Naples parking function. And so in fact, this tells you that there are more Naples parking functions than there are parking functions, right? Because now we know all the parking functions are Naples, but not the other way around. Okay, great. But knowing that is not enough, because what do we want to do as a combinatorialist? We want to count. We want to enumerate them. So this was her question. She said, how many Naples parking functions are there? So I thought, this is good, and I don't know the answer. And so let me find some students that want to work on this. So Sakaya, Alex, and Andres seated here at the front. They were students at the MSRI UP undergraduate program. So this was in 2019. And we ended up writing a paper about this. And that one's linked in the Padlet. So it's called A Generalization of Parking Functions with Backwards Movement. So they're brilliant. I gave them the question, and I think like the first week and a half, they solved it. And I was like, oh no. Also, it was not that it was easy. It is that they were brilliant. Okay, let me make that very clear, because you'll see the formula in a second and you're gonna be like, wait, what happened, right? Okay, but they did even more than what Allison asked. They said, okay, we like to generalize stuff. Why do we only need to back up one spot? What if I can back up K spots? And then I was like, well, solve the K equals 1 case first, and then we can see if we can generalize, right? I was like, solve her question first, then we'll go. But they were like, no, we got it. So here's what they did. They specify a parameter, right? So some variable. They say K. K is going to be the number of spots the cars are allowed to back up. And then they play the game. So we start with a preference vector whose entries are in the numbers 1 through n. There's n options. Okay, so the parking rule goes exactly as I described previously. The car goes to its preferred spot. If it's available, it takes it. If it is not available, it's going to check one spot at a time up to K many behind its preferred spot until it finds a spot that's available. Now, it might not have any available spots behind. Then it continues forward down the street. Okay. then it continues forward down the street. So if occupied, check one at a time up the K behind its spot, taking the first available. If all occupied, continue forward, taking the first available. So think parallel parking very badly, right? Very badly, like up to K many, like you're just like, hopefully there's no cops around. Okay. However, if all the cars can park with this rule, then we call that list of preference of those initial preference spots a K Naples parking function. How are we doing? Okay, great. You see, look at how terrible that thing is. You see how terrible that thing is? That was their result. It's hard. Okay. But I just wanted to throw it in there to show you that like the best we could do was a recursion, right? You see how this requires us knowing something about smaller number of parking functions? And then does the order of those rules matter? Yes, it does. It absolutely does. So sometimes you will get more parking preferences that allow the cars to park depending on whether you go forward or backwards first. So that's another direction that you can take, no pun intended. All the puns intended. Okay, but when they did this, they had all the questions that you're asking. They were like, wait, what if we do this other thing? Or this other thing, and this other thing? And I was like, wait, write that down somewhere. Let's solve this thing, and then we write another paper. And that's exactly what we did. So, and that's where the title of this talk comes in. So I brought on my collaborator, Josh Carlson, who was a faculty member here at Williams. He's now at Drake. And then Sakaya, Alex, and Andres came to visit me. And we wrote an entire paper where the questions were the meat of that paper. And have you ever seen these choose your own adventure books? Y'all are so young, I never know. They were like popular before you were alive, you know, because we didn't have the internet back then. So to entertain ourselves, we would read a book and then it would say like, okay, now you're being chased by a dragon. Do you fight? Go to page 78. Or do you run? Go to page 33. And then you would flip between the pages of the book, choosing your own trajectory as the protagonist. So that article is written in that fashion. You're stuck in traffic. You have Stanley's Enumerative Combinatorics Volume 1. You randomly flip a page and you find parking functions. And then you just start pondering, what if I did this? Well, what if I do this? What about this other thing? And then we tabulate a whole bunch of open problems you can work on. So I'll stop there for sake of time, and I'm happy to answer any questions you might have. But I think you saw in the chat, the kinds of questions you're asking are literally the kinds of questions that can lead to math research papers. So who can do research? You can do research because you were already doing it. All right, awesome. It's been so great chatting with everyone. I'll stop sharing and happy to answer any, well, maybe I'll leave the sharing in case you want to ask math stuff. Thank you.
Let's give a virtual applause for Dr. Harris.